did it was made a table set of values. Okay? We do the exact same thing here. So if I start with y equals 2 to the x, think about it. Just like we've done in the past, we'll take the y equals 2 to the x and just make a quick table set. We'll take a couple of these because we use them for notes and homeworks and stuff. And you want to take a look at two values that are positive, two values that are negative, and 0. That way you see what's going on both sides of the axis and what's happening at the y-intercept. Okay. Somebody's at the door. How are you, Mr. Tuna? You're in trouble. You're joking. No. Yes, I am. Don't. Anyway, so as you go through stuff like this, you're going to be using your you'll be using your exponent rules, your power rules, and things like that to simplify stuff out. A lot of times when I do these things, try not to use your calculator because a lot of times on quizzes and stuff there will be a lot of calculator, non-calculator things. So you'll start to pick up on how things set themselves through. So you've got 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the 1, and 2 squared. Well, those are pretty easy to do, right? What's 2 to the negative 2? 1/4. 1/4. 1/2. What's 2 to the 0?
1.
1. 2. 4. So what's happening here is we get a curve. Okay. Just real easy values to plot through. 1/4, 1/2, 1, 2, and 4. Now, what I want you to do is think about, will this value ever become negative? No, and why is that? Yes, sir.
It will always be a positive fraction because it's divided by the.
Right. Because what's going to happen here is you're going to be getting closer and closer and closer to 0, but will you ever get there? So when you get closer and closer to something, but you don't touch that something, what does that create? An asymptote. Good. You wind up with an asymptote then at y equals 0. So your curve is increasing going from left to right. Now, do I have a domain restriction? No. Which is it? No. No, correct. There is no domain restriction here. So domain here would be all real numbers. What about my range?
You do have a restriction.
What is it? So my range, though, now think about it. It can't equal 0, but is it going to be negative?
Y has to be greater than 0.
Correct. It's got to be greater than 0.
Yeah.
Okay.
That's right.
It's going to be all values of y that are greater than 0. And you'll see this a lot. It's going to ask, you'll start to see domain and range questions. Exponential growth, exponential decay. Either one of those will not have domain restriction, but they could have range restriction because of the asymptote. Okay? And it depends on what side of the curve it could be increasing or it could be decreasing. Yes, sir?
Isn't there a point though where like the graph is going like so far up for each like domain that like it doesn't really go anywhere, it's just going straight vertical?
But it's still it's not going vertical, it just has a higher rate of change.
Okay.
Okay, it's never going to be vertical because you're always going to have a horizontal component to it.
Right.
If it was vertical, you'd have no horizontal component
You're right. Okay.
between the two values. And that's a good question because we actually do stuff like that in pre-calc, where we can find the change in, what did they, I said it earlier, what did I call it? You were there for an hour, you remember?
What?
Exactly.
Yeah.
Average rate of change, it's a derivative.
Okay.
You do that pre-calc.
So like there's nothing for when the x just starts going like almost vertical.
It just has a quicker rate of change, that's all.
Okay, all right.
That's all it really becomes. So what I want you to do then real quick is I want you to take out your calculators and I want you to do this into 3 separate y equals tables. And those of you guys with the color ones are going to be like, sweet. Because it'll look really cool because you'll see 3 different colored graphs. I want you to put 3 to the x, 4 to the x, and 5 to the x. And see if you notice anything special. What do they all have in common? They don't touch 0, good. What else? They're all increasing going from left to right, okay? Yes, this is an exponential function, very good. They all meet at 1, good.
We already established.
Just like she's taking math twice.
Students now.
No, I don't. But I'm building you back up. What happens here is that you get this generic form of y equals a times b to the x. What was happening with our 3 functions we just did, we had y equals 3 to the x, y equals 4 to the x, and y equals 5 to the x, is that that value of a wasn't shown because the value of a was 1. What's happening here is that you're getting y equals 1 times 3 to the x, y equals 1 times 4 to the x, sorry, y equals 1 times 5 to the x. That value of 1 in each of those graphs was shown to be what on the graph? The y-intercept. You wind up with the y-intercept. So here's what we get. We start to be able to work with these, what we're going to call a generic form of a parent function. So this is going to be our parent function, where a is the y-intercept. And where was our horizontal asymptote at all of these? 0. And y equals 0 is the horizontal asymptote. Okay. When we have this generic form, this parent function, y equals a times b to the x, that stuff always holds true. Right? It will always hold true. The value of a is some scalar. Okay? That value of a is just going to wind up being some scalar. Because if you think about, if I put in y equals 2 times 3 to the x, order of operations, if you start putting in values, tells you to take 2 times 3 to the negative 2. What would you have to do first? The exponents. So you get 1/9 and so on. But yet when you get to 3 to the 0, what's 3 to the 0? What's 1 times 2? 2. So this value of a is always going to wind up being your y-intercept.
That's easy.
Yes, sir.
Now, can like at the end of this equation you have like a -1 or a +1 or anything like that, just like
Yep.
every other graph?
Just, and that's where I'm leading to.
Okay.
That's where this is your parent function of the shifted form with your h and your k.
Okay.
And that's what this is all getting to. What we always start with, and you're going to see parent functions and shifted functions with the h's and the k's all throughout second semester. Oh yeah, I forgot to tell you guys what we do second semester. We start with the exponent stuff. This will take us, I don't know, 3 weeks or so maybe? 4? Or something like that. And then we get into trig. and we'll be in trig for a long time. We're basically going to do all of chapter 13, all of chapter 14. That is what, just like how last semester, one of the major things that we did was factoring and polynomials and all that kind of stuff, finding zeros and everything. Trigonometry is the huge, big granddaddy of them all for Algebra 2 classes. The trig stuff is not only doing what you guys did last year with your right triangles, but taking it a step further in, you guys did law of sines, law of cosines, correct?
Yeah.
Law of cosine, yeah. You guys did law of sines, law of cosines. You worked with tangents, sine, cosine, tangent. You found the missing angles and things like that. What we do in Algebra 2 then is with law of sines, there is a possibility that it doesn't always work. You could have no triangle that shows up. You could have two triangles that could happen. It's called the ambiguous case. We introduced that. We introduced law of cosines with the ambiguous thrown in there. There's a lot of formula junk that works itself through. After that, then we start to get into that unit circle. And the unit circle stuff that I'm sure you guys have seen, and people are already worried about it. It's just built off of the two special right triangles, 30, 60, 90, and the 45, 45, 90. If you remember how to work with those two triangles, the unit circle is ridiculously easy because everything is built off of that. And if you know what quadrant things are positive, things are negative, it's even easier. Once you master that, which believe it or not, you will, when we do graphing of it, again, there are going to be AH's and K's with the graphing of sine, cosine, and tangent. We might, depending on time, we might graph the inverse functions, secant, cosecant, and cotangent as well. So it's just one extra step after graphing a normal. There's a lot of little things that we do in trig. After that, we do, I think we're going to do sequences and series, and then we do the probability statistics towards the very end. Probability and statistics is generally a lot of fun because it's a lot of playing cards. Not card tricks, but we're going to be playing cards and looking at different probabilities and algorithms and stuff we can work with.
Teach us how to win a blackjack.
Yeah, we do stuff like that. We talk about, you guys heard about the bell curve and normal curve?
I've never lost a game.
We talk about how you do work with standard deviations and all that kind of stuff. I try to bring in some of the stats stuff for you guys because not everybody in here is going to want to take a stats class in high school. You'll probably wind up taking it in college. But at least you will see some of it before you get to college because no matter what, you're going to have to take a stats class in college just about for any major nowadays. But that a lot of it deals with working with starts out with the normal curve and how those things derive and how everything goes through it. I think that's about all we'll have time to do. There is some modeling unit we're going to try and go through, but we'll see if we have time. Don't ever do that again. Please. We don't need to frighten everybody. It wasn't you. Anyway, so let's look at what happens when we throw this in. Like I said, the parent graph here, we're going to have, for today, to start with, for being a growth model. Growth is when b is greater than, what did I write it up? Greater than 0 and not equal to 1. Because if it was equal to 1, what's 1 to any power? And we'd get a horizontal line and we wouldn't be able to do exponential form with it.
Correct. And so it's not growing.
It's stagnant. And this gets us to the shift, the AH and the K. All right. This gets us to our shifted function. I try to put it a little dot in there. What happens here with our shifted form of a exponential growth and or decay? Y equals a times b to the x minus h plus k. Now, the value of a is no longer the intercept because there's a shift involved to it. What we do is we will plot the parent, then shift it. Your H and your K stands for your horizontal and your vertical shift, just like it always has. And if you think about it, yes, sir.
Why did they use the letter K as a variable vertical? Oh, okay.
Actually, if you think about it, or if you go really go into it, why you use K? V, velocity, E button, R, radius, T, time, I is imaginary, C is a constant, A squared, B squared, C squared, line.
That had no other letter.
Why not see that?
Same thing with slope. S looks like a 5. L, line. O, 0. P, probability. E, they just went through the letters.
Why don't they like E?
Yeah.
What? Wait, Mr. Murphy, I didn't catch the reason why they don't like E.
E is an exponential. Is the exponential value e to the x?
Oh yeah.
What, JC? Do you think I'm pulling their legs?
I don't know. Just like I guess.
Huckleberry Finn dies.
No,
What?
it's not.
Spoiler alert!
Oh, sorry. I'm sorry.
Hey, Mr. Murphy! Hey! Han Solo died.
Hey! That was young, sir! Does he not see all the...
Do you honestly think I know what happens in Huckleberry Finn?
Yes.
He kills Tom Sawyer.
It kills Tom Sawyer, yes. And there were water skiing behind the paddle boat going up the Mississippi.
And they were writing.
Think about what he
No,
just
while they're
said.
singing Old Man River. No, I don't know. Anyway. Now, let's go back to where your parent function. Yes, sir.
So how do you know that like the exponent is like is having a value subtracted?
It'll be written. I'll show you an example.
Okay.
Go back to your parent function. Where was your horizontal asymptote?
Hey. Just kidding.
It was at y equals 0. Now, your k value shifts everything vertically. So in a shifted function, where's your horizontal asymptote?
Okay.
It'd be at k.
Oh,
One thing you can say for certain is that y equals k is the horizontal asymptote. Y equals k is the horizontal asymptote. Let me show you an example then. And we'll walk through how we piecemeal it all together.
Oh, okay. Now I get it. Oh yeah, that makes more sense. All right.
And that's what it would look like.
Yeah.
Sometimes you'll throw it in parentheses, sometimes it doesn't.
Yeah, because I forgot that thing was it's the exponent's always written as an x.
Yeah, that's what I was
equation.
thinking too. I was like, how do you know what it is?
Yeah, the exponent will have the exponent. This is y equals that.
And you'd be able to tell when it's graphed too because it would be shifted.
Right.
To that. Okay. All right. That makes much more sense.
So if you have a function y equals 3 times 2 to the x minus 1 minus 4, what we like to do here for each and every single one of these types of problems is I'm always going to identify what my parent function is first. Now, in this case, my parent function is that. 3 times 2 to the x. Basically, your parent function is everything less the h and k. Okay? Now, with that, I know where my y-intercept is, and I know where my horizontal asymptote is. I also can make my quick table set of values.
Hey, Mr.
Yes,
Murphy,
sir.
Quick question. X minus 1, is
Mhm.
that separated so it's x and then -1, so it doesn't have anything to do with the parent function, or like?
The parent function is just 2 to the x. This is the shift x minus h minus k in this case. So that means my h value is going to be 1 or -1 for h? 1. And what's k? -4. Remember the rules when it was minus h or plus a k? It was minus h, it's always the opposite of what it's written. So here it's x minus 1, so that means the h value is 1. The k value, since it's plus k in the generic form, you are subtracting 4, so it means k is -4. So if I go back to my parent function, I'm going to pick those 5 points real fast, that -2, -1, 0, 1, and 2, because they're the easiest numbers to work with. Okay? They're always the easiest ones to work with. And you just go through the order box. And I get those values. 2 to the -2 is 1/4. So 3 times that, we get 3/4. I get 3/4, 3/2, 3, 6, and 12. You okay with that? I know that this is the parent function, therefore it has a horizontal asymptote where? At 0, good. So I know right away I have a horizontal asymptote at y equals 0. And I just substitute my points now. At -2 is at 3/4. Three halves is 1 1/2. 0 and 3. 1 and 6. And this would be at 2 and 12, so it's just a little bit off our graph. Now, do you remember when you've done, yes sir?
Wait, so if x is 0, wouldn't it be 3 times 1/2?
Ah, what's 2 to the 0?
But it's 0 minus 1.
I'm doing parent function.
Oh, okay, sorry.
Always, and that's one of the things that I tend to do is I always do parent functions first before shifts because I won't make those silly mistakes. Yes, it takes an extra minute to do it this way, but it forces you to make sure you do it right. When you guys do a parent function, it's a graph that is not technically there. You're graphing a sketch of the parent prior to the shift. So when you graph something that's not technically there, should you draw it with a solid line or a dotted line? So we just draw this as a dotted line. Now to each one of those values, I have an h and a k. I move them right 1 and down 4. Right 1, 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 down 4. This was at 12, so this one would be at 8. And then lastly, I got to replace my horizontal asymptote. Where does it go? At -4. And I graph my parent function. Oops, a little close. Okay, close enough. Okay? And that gives you the idea of what these things are going to look like.
Oh, you have to use the asymptote.
Yep. Yep. And your asymptote on your shifted function will always be at whatever your k value is for these. Okay? Now, the only real difference between a growth and a decay problem is that a decay problem, your value of b is smaller than 1, but bigger than 0. That's the only difference between a growth and a decay problem. Oh, did I meant to. I'm supposed to be greater. B was supposed to be greater than 1. I'm sorry. I didn't realize I did that. I'm sorry about that. I'm sorry. Right, because if it was 1, that's why it's just greater than 1. Yes, sir.
That's for growth.
Yeah. I'm sorry. I totally brain farted on that. Sue me. Well, not really.
First day back.
First day back. Yes. Yeah, I made it all day without. Oh no, I didn't. Say I screwed up to recalculate. I forgot what tangent something was.
Mr. Beck.
Yeah, I was just gonna say, he's,
I made up for it, right?
his
Yes,
badge
ma'am.
is.
There's really nothing from first semester that correlates back to second. You will use the exponent rules and stuff like that. You don't need any of the quizzes or tests or any of the homework or that kind of junk. You really won't need any of that. Yeah, I mean, there will be some stuff that will come back into play. I mean, you're still going to have some factoring problems. You still have some of that stuff here or there, but not like a majority of it will be back and forth. You don't need it. You really don't. Are you really going to go back and look for it?
No, like I have it here, I just don't want to carry it around.
Oh, I got you. No, you don't. So what happens then if we look at a decay? Let's try a different one. Let's try one with a decay. Let's jazz this up a little bit. Let's throw in. I have 5 times 1/2 x plus 3, then plus 2. And in this case here, what happens when the value of b is between 0 and 1, the direction of the curve is going to is different. Okay. So what we do here is basically the exact same thing. Our parent function is still going to be y equals 5 times 1/2 to the x. The parent function ab to the x doesn't change between growth and decay. They still are the same. We still use the same set of values for quick substitutions, the -2, -1, and so on. This out of the way for a second. What's 1/2 to the -2? Four. Remember, it's unhappy. Flip it. It's happy. What's 4 times 5?
20.
Yeah. What's 1/2 to the -1? 2. Remember your exponent rules, guys. You're forgetting these things. If it's 1/2 to the -2, that means it's 1 to the -2, 2 to the -2, which means it's 2 squared over 1 squared. So what's 1/2 to the -1? 2 times 5 is 10.
The answer is irrelevant.
What's 1/2 to the 0?
1.
What's 5 times 1? What's 1/2 to the 1? What's 5 times 1/2?
2.5. Infinitely
And then 5/4.
There are
Okay.
infinitely no solutions.
So what's happening here is it's just going a different direction. At -2, you're way up at 20.
Why did the graph do that when you jump?
That felt good.
Oh, did you?
It went up over here.
0 and 5, there's your intercept. Get it? Your intercept is still at your value of a. 5/2, you said so eloquently, 2.5.
2.5.
I don't know what this decimal thing you're talking about is. 5/4 is 1 1/4. And what is it approaching as far as the asymptote is concerned? 0. I'm looking at the parent function. This one is decreasing from left to right. So what happens here when you have decay problems, if A is positive, let me write this, A is greater than 0, your graph is going to do this. If A is less than 0, it reflects itself. Yes, ma'am.
How come it's not above?
Yes, I'm sorry. I forgot that we had a shift to begin with. Yes, this should have been dotted. My fault. Okay. So you have two different forms of what decay will look like. Decay, if A is positive, is going to be decreasing from left to right. If A is negative, it'll be increasing from left to right, starting negative and working its way up. Same deal with growth. Growth, if A is positive, it's increasing like that. And then if it's negative, it's reflected going the other way. It's nice to know the direction of where these things are going to go. So if you start plotting it and you wind up going the wrong way, you know you've done good. Yes, sir.
How do you still consider growth the y is going down?
The growth and growth and decay is defined by the value of B, not the value of A.
Like in an actual application, even if the value went down, if B was positive.
Yeah, and that's where the growth rate and decay rate come into play, because the B value is going to be 1 plus some rate, which is a percentage, versus decay rate, which is 1 minus that same rate. So it's either going to be greater than 1 or between 0 and 1. And that's where this all comes into play. Okay. Do you guys have something? Sure. So now we go back to this one. We had our H and our K here were 3. Was it, if it's plus 3, is my H 3 or negative 3?
Negative 3.
And then K is at 2, so what's my K value? 2. So what do I do to all of those points?
Down 3 over 2.
Left 3, up 2.
That's what I meant.
Good. So everything just gets moved left 3 and up 2. And it would look like that. And notice your vertical or your horizontal asymptote also moved.
Yep.
Put your feet down. And it moved to your K value. Yes, now it should be a solid line, but I just cheated by moving my graph. It is.
Can we do that?
Nope.
Why not?
You have that transparency paper? Okay. Have you guys ever used an overhead?
Yeah.
Pretty soon that'll be like a. Have you ever used a tape deck?
A what? Yeah, I've used a tape
I
deck.
know what that is. I know what that is. And what is it called?
You're messing.
I probably would have if I knew it was a tape deck, or if I saw it.
Yeah, tape cassette.
Oh, okay, that's what it is. Wow, I have one. I just don't know what it's called. What? A tape deck. It plays cassettes. Yeah.
All right. Do this one. Graph a. Well, first of all, is this growth or decay?
That's okay.
It's decay. Why is it decay? Less than 1. Good. Now, what happens if it's 3 halves? Would it be growth or decay? Growth, because it's still greater than 1. Okay. That's how, like Carter was asking here a second ago, why is this one not growth? Because it's increasing from right to left. Why is this one not decay? Because it's decreasing from left to right. Well, what's happening here is the value of A does not define growth or decay. The value of B, defines whether or not it's going to be growth or decay. If B is greater than 1, growth. If B is between 0 and 1, decay. And that works all the time. And that's we get into what things are called growth rates and decay rates, growth model, decay model, things like that, it's really easy to see how it works because of the percentages and things like that. So take a second, do a parent graph and a shift, and we'll call it a day.
Sounds good.
Go through this real quick. Hopefully, you have your parent function of -3, 1/2 to the x.
Why is it called
Parent function? Yeah. The parent function is what is this graph made of? This graph started out like this, but it moved.
I don't know why is it called
Because it's an offshoot of something else. Like you are an offshoot of your parents. It's a combination of horizontal and vertical shifts, whereas you're a combination of your mom and your dad. I'm trying my best to figure out why it's called that, but I don't know. You know what? We're gonna run out of time. I need you to write down the problems. Is this terrible?
No.
Yes.
Oh my goodness. I'm
Now you'll get
probably
over it.
going to need to see a counselor because of this.
So there are 2 sets here. It's the same problems for both 8.1 and 8.2. There's only 8 graphs that you have to do. Okay. 4 of them are just parent function, and 4 of them are going to be with the shift. So you have to do your H and your K shift to it. You'll find out real quick. It is really fast. Those first problems, the 14 through 24 in both those sets, I believe, are identify the y-intercept and where your asymptote's going to be, whereas the other ones you'll have to go from there. Okay. We'll build off this tomorrow and probably jump into the 8.3 stuff of e to the x and how do we graph that. It's actually even quicker than these because there's less points that you have to use. Yeah, after we go through all 3 of these sections. Then we'll reset it and start with the word problems. Which will probably, wait, today's Wednesday, right?
Yeah.
I don't either.
Yes.
It's one of those weeks, I know. So
Today is
we'll
definitely
probably do the word problem stuff on Friday. And this will go off those 3 sections. Okay.
Oh shoot, I forgot to write down evens. That would have been bad.